Alright, so in the next two videos we're going to explore a method for computing the inverse of a matrix using determinants. This method comes with a warning, we'll put this right up at the front, that this method for computing the inverse is less efficient than the method you already have. Okay, it's less efficient than the method using row operations. Okay, so for a 3 by 3 matrix, I would say that the amount of work is more or less equivalent. Once you get to 4 by 4 matrices and higher, this method of computing the inverse is going to be far more work, and it's probably not what you want to do. But it does have a number of uses. And one of the uses you would find for this method is if you were trying to compute the inverse of a matrix that, let's say, had variable entries, functions in it, things like that, because it will allow you to sort of, avoid doing row operations, right? If when you're doing row operations, you might end up having, you might have to multiply by 1 over something to clear something out from a row. And, if you're dealing with functions, dividing by a function is a concern because you might be, there's going to be some values where that function might be 0. You got to worry about dividing by 0. So we don't want to worry about that. Okay. So the first step here to coming up with this formula is we introduce what's called the adjugate matrix. Okay. So the way you form this adjugate matrix is you start out by calculating all the cofactors of your matrix, right? So this is more work than simply computing a determinant, because to compute the determinant we only have to calculate cofactors along one row. So for like a 4 by 4 matrix, we're already doing 4 times as much work because we're calculating all 16 cofactors, not just 4 cofactors along one row. Okay, so we calculate every cofactor for our matrix, all right? And each cofactor gives us a number, and there's one for every entry. So if we had an n by n matrix before, we get a new n by n matrix whose entries are those cofactors. That puts us here. Okay. Now, the cofactor matrix turns out to be not exactly what we want. We actually want the transpose of this thing. So we take the transpose of this cofactor matrix, and we get what's called the adjugate matrix. Okay. So the adjugate matrix we're going to see it's actually almost the inverse. It's actually a scalar multiple of the inverse, and that scalar multiple we'll see involves the determinant of the original matrix. Okay, so here's an example. Let's do, like I said, this gets ridiculous for 4 by 4 and higher, so let's do a 3 by 3 example. Okay, so we take let's do a 3 by 3 example. 2 minus 1, 3, 0, 4, 1 minus 2, 1, 5, let's say. Okay, so let's start calculating cofactors. The 1, 1 cofactor is going to be 4 times 5 minus 1, so it's 19. It comes with a plus sign. There's not really room to write everything out here, so you guys are going to have to bear with me as I kind of try to calculate these things in my head. So the 1, 2 cofactor, we're deleting row 1, column 2, leaves me with these entries here. 0 times 5 is 0. Subtract 1 times minus 2. So minus 2 gives me plus 2, but remember that that cofactor comes with a minus sign, so actually I get minus 2. So it's there's a minus 1 to the 1 plus 2 times the minus 2 coming from that determinant, or sorry, times the plus 2 coming from that determinant. Overall I get a minus 2. Okay? 1, 3 cofactor comes with a plus sign, and it's going to be 0 times 1, 4 minus 4 times minus 2, so minus 8 gives me plus 8. Okay. 2, 1 cofactor comes with a minus sign. Okay, the minus sign here, remember the signs overall, they go plus, minus, plus, minus, plus, minus, plus, minus, plus. So if I delete row 2, column 1, I'm left with minus 1 times 5. That's minus 5. Subtract 1 times 3. So minus 5 minus 3 gives me minus 8. Okay. Minus 8 gives me plus 8. 2, 2, plus sign out front, and if I delete row 2, column 2, I'm left with the guys on the outside, so 2 times 5 is 10, 3 times minus 2, that's minus 6, 10 minus minus 6 gives me 16, 2, 3 cofactor, so I'm deleting row 2, column 3, 2 times 1 is 1, and so it's 2, and then minus 1 times minus 2, okay, is also 2. So it's 2 minus 2 gives me 0. So there is a minus sign out front for this one, but it's 0. So minus 0, of course, is just 0. Alright, and now we've got to do the last row. So let's do those up here. The 3, 1 cofactor, okay, comes with a plus sign. 3 plus 1 is even. And it's, so if I delete row 3, column 1, I'm left with this 2 by 2 determinant here, which is going to be minus 1, minus 12, so minus 13. 3, 2 cofactor, minus sign out front. If I delete row 3, column 2, I'm left with 2 times 1, minus 0, so 2. Minus 2, because of the minus sign out front. Okay, and finally the 3, 3 cofactor. I'm deleting row 3, column 3, leaves me with this guy. It's a plus sign out front. 2 times 4 minus 0 plus 8. Okay, so I've got all my cofactors. So now the cofactor matrix is, along the first row, 19 minus 2, 8. Along the second row, 8, 16, 0. Along the third row, minus 13, minus 2, and 8. And that means that the adjugate matrix is, so I take the transpose, 19 minus 2, 8. First row becomes first column, 8, 16, 0. Second row is the second column, minus 13, minus 2, and 8. Third row becomes the third column. And we've got our adjugate matrix. All right. Now, if you want to get some idea of why this is useful, we can try multiplying these guys together. Let me see. Was I planning to do that? I'm not planning to do that yet. So let me show you what happens when we multiply these. Okay. So one thing we might do. Let's make a couple of observations. So let me erase. Let me erase these guys. We don't really need them anymore. We've worked that out. There we go. Oh, missed a couple spots. So one thing we might notice is if I wanted to calculate the determinant, I've got my cofactors, so let's do my cofactor expansion, right? If I did my cofactor expansion along, I don't know, pick any row you want, first row, 2 times 19 minus 1 times minus 2, 3 times 8, 38 plus 2 plus 24 gives me 64. Okay, you could check that would work. I guess maybe the right one would have been to do along the second row, right? 0 times 8 plus 4 times 16 plus 1 times 0. But again, 64. Okay, so the determinant is 64. And here's what's interesting. Calculate A times the adjugate. Okay, so do 2 minus 1, 3, 0, 4, 1, 2, 1, 5, and then 19, 8, minus 13, minus 2, 16, minus 2, 8, 0, 8. Okay, So we do that, and notice when I do first row times first column, 2 times 19 minus 1 times minus 2, 3 times 8, that's exactly what I just did up here, 64. Row 1 times column 2, 16 minus 16 plus 0, I get a 0. Row 1 times column 3, minus 26 plus 2 plus 24, 0. Now, row 2, column 1, 0 times 19, 4 times 2, minus 8 plus 8. So 0 minus 8 plus 8, 0. Row 1 times column 2, well, that's the cofactor expansion along the second row. 0 times 8, 4 times 16, 0 times 1, 64. Okay. And if I do row 2, column 3, 0 minus 8 plus 8, 0. Now, row 3, column 1, minus 38 minus 2 is minus 40 plus 40, 0. Row 3, column 2, minus 16 plus 16 plus 0, 0. Row 3, column 3, 26 minus 2 takes me to 24 plus 40, 64, which is 64 times the 3 by 3 identity. It's the determinant of A times the 3 by 3 identity, right? So if these guys had, so if determinant of A is 1, I would have a product equal to the identity, and I would say, oh, those guys must be inverses of each other. It's not quite equal to 1 because there's a 64 out front, but that's okay. We can divide by 64 on both sides, right? We could put that 1 over 64 over on the left, and this gives us some hint that this adjugate matrix and the determinant, those have something to do with the inverse. Okay, so here's the formula. The inverse, as long as the determinant is non-zero, we know that A is invertible. We did that on a previous video. But now we can also write down a formula for the inverse. We compute this adjugate matrix, and then we multiply by 1 over the determinant, and we've got the inverse of our matrix. Okay, 1 over the determinant times the adjugate. We can see that in our example here. If I had done, if I had just done this, if I had done A times 1 over 64 times the adjugate of A, I would get the identity matrix, right? And 64 was the determinant, right? Because that 1 over 64, I could bring that out front. If there's a 1 over 64 in front of this product here, I would have a 1 over 64 here, would cancel the 64, leave me with the identity, right? And we know that as soon as you multiply two matrices together to get the identity, well, that means they must be inverses of each other, and that gives us this result. Okay. In the 2 by 2 case, you probably saw this formula in the textbook. One of the reasons why I didn't emphasize this formula back then is that it only really works in the 2 by 2 case. For a 2 by 2 matrix, this formula is probably faster than doing row operations, but you've got to memorize a formula. For 3 by 3, I would say for a 3 by 3 matrix, if you're good at calculating those cofactors in your head, this might be marginally faster than doing row operations. Once you hit 4 by 4 and higher, though, think about what it would mean to use this formula for a 4 by 4, right? For a 4 by 4 matrix, you would have to calculate 16 3 by 3 determinants plus 1 4 by 4. Okay, that's a lot of work. 16 3 by 3. Who has time to do 16 3 by 3 determinants, right? So it's not a very practical formula for larger matrices, but it is it's theoretically useful in a lot of situations. Okay, so let's do one more example. Why not? Let's do A equal to 2 minus 1 3. 1 4 2 0 1 1. Okay, so I'm going to calculate these cofactors. I'm going to do this fast because I don't want this video to get over long. 1 1 cofactor, 4 minus 2, 2. 1 2 cofactor is 1 minus 0, but it comes with a minus sign, so minus 1. And the 3 cofactor is a 1, and then -1 minus 3 gives me -4, but there's a minus sign there, so 4, and then 2 minus 0, 2. 2 times 1 is 2, minus 0, but it comes with a minus sign, minus 2, -1 minus 2 minus 12 is minus 14. That one comes with a plus sign. In the middle here, 2 times 2 is 4, minus 3 is 1, but that guy gets a minus sign, so minus 1. And then finally 8 plus 1 is 9. Okay, so the adjugate of A is going to be 2 minus 1, 1, 4, 2, minus 2, minus 14, minus 1, 9. The determinant of A, if I did, let's say, well, you know what, the bottom row is probably the easiest one, right? 0 times minus 14 plus 1 times minus 1 plus 1 times 9 is 8. Okay, and so that tells me that A inverse should be, well, it's 1 over the determinant of A, which is a number, remember, times the adjugate. So it's 1 over 8 times this adjugate matrix. So 1/4, 1/2, minus 7 over 4, minus 1 over 8, 1 over 4, minus 1 over 8, 1 over 8, minus 1 over 4, and 9 over 8. And that should be my inverse, okay? And I'll leave it as an exercise for you to check. Make sure I didn't mess up, because I did that pretty fast. There's a good chance I made an error, an arithmetic error somewhere. Check that if I do A times the adjugate of A, I get 8 times the identity. Okay? That would verify that my work here is correct. All right. Quick sketch of the proof. I'm not going to spend any time on this because I don't want this video to be any longer than it is. Because you take the transpose, right, when you form the adjugate, notice that the first column gives you the cofactors along the first row. So when I do the first row of A times the first column of the adjugate, right, that's the cofactor expansion along the first row, right? This times that. That's the cofactor expansion along the first row, and so I know that the 1, 1 entry in this product is going to be the determinant. Similarly, second row times second column is going to be cofactor expansion along the next row, okay, and all the way down. So it's easy to see that the diagonal entries have to be the determinant. Why are the off diagonal entries equal to 0? Well, the easiest way to see that is that you're kind of taking the coefficients along one of the rows and you're multiplying by the cofactors along one of the other rows. That's kind of what you would get if you say copied down, if I took so doing, let's say, row 1 times column 2, that would be like taking the determinant if I had scratched out row 2 here and wrote another copy of row 1, and then did the cofactor expansion for that matrix along row 2. But we know then, well, that matrix would have 2 rows that are the same, and we know that any matrix that has 2 rows the same has 0 determinant, right? So the off-diagonal entries are basically 0 because each of the off-diagonal entries is computing effectively the determinant of a matrix that has 2 identical rows, and that determinant should be 0. And that's why this works, right? So then I can multiply both sides by 1 over the determinant, and that gives me my formula. Okay.